All right, week 5, lesson 2, nitrogenase. Now that we know the structure, let's figure out the mechanism for how dinitrogen is reduced to ammonia by the nitrogenase enzyme complex. A detailed kinetic model was developed during the 1970s and 1980s as a result of extensive experimental work on the iron molybdenum cofactor. This model is known as the LT kinetic scheme, which is named after the groups of Lowe and Thornley, who did most of the work on this mechanism. There's a series of 4 proton and electron transfer steps. These are actually a common research area right now, proton-coupled electron transfer, where the proton and electron go together. Anyway, these 4 proton and electron transfer steps reduce the FeMoCO state from E0 to E4. The E4 state is referred to as the Janus intermediate. This is after the ancient Roman mythical figure who looks both forwards and backwards. Backwards to the past, forwards to the future. This intermediate, E4, is the species that binds dinitrogen, and this is the state where the obligatory release of dihydrogen is observed. You can see that as drawn, it's a reversible step. The addition of hydrogen catalyzes the loss of N2, going backwards towards the Janus intermediate. It's clear from this model that in order to reduce N2 to 2 ammonias, a total of 8 electrons and 8 protons are required, 6 of each for the nitrogen and 2 for the molecule of dihydrogen. Each electron transfer step takes an electron from the Fe4S4 cofactor in the iron protein. That electron is delivered to the FeMo cofactor. So there have to be a total of 8 separate docking and undocking steps in order to fully populate this species with the 8 electrons. Each docking step results in the cleavage of both ATP molecules in the iron protein. So a total of 16 ATPs are cleaved to transfer the 8 electrons and protons. So this kinetic model accounts for the rates and the chemical steps required, but a detailed model that explains the structure and the mechanism took quite a bit longer, almost 30 or 40 years longer. So the exact details of the process are still not known with certainty, but a model has been proposed that is consistent with all of the observed experimental data. So our goal is to explain the function of the ATP binding site in the iron protein and explain why and how dihydrogen is lost obligatorily during this mechanism. It turns out not very much is known about the first 3 states, E1, E2, and E3. They've all been studied by EPR. There are rates of the formation of these 3 different species have been observed and measured, and Mossbauer spectroscopy, other spectroscopies have been used. The first step is a reduction step, the second step is an oxidation step, and the whole cycle cycles between only 2 formal oxidation states of the whole cluster. The reducing equivalents are stored as hydrides. This was all proposed, and subsequent studies supported this hypothesis that hydrides are the source of electrons of reducing equivalents in this model. So let me orient you to what we're looking at here. On the left is a zoom in of the FeMo cofactor showing some nearby amino acids. And on the right is the Janus intermediate and a ChemDraw picture of what that Janus intermediate looks like. The first intermediate that is well understood is the E4 state, the Janus intermediate. This state has been trapped and observed by EPR and Endor spectroscopy. It shows strong coupling between the electrons and the hydrogens in this complex. The details of the structure suggest that there are metal-bound hydrogens, metal-bound hydrides, and they are believed to be bridging between 2 different metal centers instead of only on a single metal center. So the details of the EPR show that. Endor spectroscopy on molybdenum gave evidence that the hydrides were not on the molybdenum, but instead were on the iron atoms. Some of the early proposals, and by early I mean only like 5 or 6 years ago, suggested that both hydrogen atoms were bound with a terminus on iron 6. Several structures for this intermediate with hydrides bridging several different iron atoms have been postulated. Quantum mechanics calculations support only a subset of those postulated structures. And finally, high-resolution Endor spectroscopy and quantum mechanical calculations in concert gave this as the structure of the Janus intermediate. It does have two bridging hydrides, though the hydrides bridge iron 6 and iron 2, and iron 7 and iron 3, as shown in this picture. At this stage, at E4, 4 protons and 4 electrons have been inserted into the cluster. The bridging hydrides account for 2 of the protons, but all 4 of the electrons, counted them as H minuses. The remaining 2 protons, shown in green here, are placed on nearby sulfur atoms for electrostatic stabilization. So we have minus and plus charged species nearby each other to reduce the net charge on the complex. So the first part of this mechanism, from E0 to E4, is the accumulation of reducing equivalents stored as hydrides. Dinitrogen binds to this stage, hydrogen is lost, and then steps E5 back to E8 and E0 are subsequent hydrogenation steps in a productive fashion to generate the ammonia molecules. So the Janus intermediate here is the linker between the first part where reducing equivalents are collected and the latter part where productive chemistry is taking place. In the absence of the dinitrogen substrate, this process will still go through to form the Janus intermediate. It then releases dihydrogen, which I'll talk about on the next slide, and it regenerates the E0 state. So these are non-productive reducing equivalents that take place when dinitrogen is not present in the pocket, the binding pocket for the enzyme. The most challenging part of the entire process is the binding of dinitrogen to form first the dinitrogen complex, and then the first reduction to form the coordinated diazine, H2N2. It's now believed that the enzyme uses some things that we learned from our organometallic chemistry unit. A reductive elimination of the dihydrogen generates a, quote, super reduced, end quote, iron core that involves iron atoms 2, 3, 6, and 7. Note that in this figure, which is from a slightly earlier paper, both of the bridging hydrides are shown touching iron 6 instead of 2, 6, 3, 7. So what is believed to occur is the two hydrogen atoms do a reductive elimination. That takes away 2 of the reducing equivalents and both of the hydrogen atoms, leaving 2 of the reducing equivalents on that 4 iron center. And you can think of it as just being on that iron 6. They're certainly free to move around a little bit. So much like carbon monoxide and olefins bind more strongly to low valent transition metal centers, this reduced iron atom is a strong pi donor, and it formally reduces that dinitrogen to diazine as it binds. And conveniently, there are 2 nearby hydrogen atoms on those sulfurs, and those 2 hydrogen atoms can protonate the diazine to give the diazine adduct here. I feel like I just misspoke, so I want to say it again. The dinitrogen complex is bound to the super-reduced iron, which formally reduces it to a diazine anion. The 2 protons from the sulfurs then protonate the diazine anion to make the diazine intermediate adduct, shown here. It turns out that the diazine binding here is reversible. In the presence of dihydrogen, this can cause the release of dinitrogen. So you can add hydrogens to oxidize, to do an oxidative addition and regenerate that E4 state. All right, so now we've got the dinitrogen bound to the FeMO cofactor, and the mechanism of ammonia production was a subject of a lot of debate. There was both a distal and an alternating pathway that were proposed. In the distal pathway, once the dinitrogen is bound, the terminal nitrogen atom is removed by 3 subsequent protonolysis electron transfer steps, so proton-electron transfer steps, and that removes 1 ammonia, and then the second nitrogen is removed in 3 additional transfers. In the alternating pathway, hydrogen atoms are added pairwise, forming diazine and then hydrazine, and finally two ammonia molecules. The evidence for the alternating pathway came from both kinetic and spectroscopic studies, also some chemical studies. So the reduction of dinitrogen, diazine, and hydrazine all give rise to the same late-stage intermediate, and that suggests that these three substrates can enter the catalytic cycle at their appropriate stages, but then just enter into the pathway and undergo the rest of the reaction at the same rate. The distal pathway would not give the same rates for these three different substrates because you don't have a diazine or a hydrazine intermediate. Instead, you go and protonate off that terminal nitrogen to make the nitrido intermediate. So this then is the complete structural mechanism that accounts for all of the observed spectroscopic data. It's consistent with the reactivity studies, the kinetic studies. It shows the importance of that reductive elimination and obligatory formation of dihydrogen. This mechanism shows both hydrides binding to the same iron. Again, this was a slightly earlier paper, but the net results are the same. We accumulate reducing equivalents from E0 to E4. The E4 is the Janus intermediate that's poised and ready to bind to dinitrogen. Dihydrogen is released in a reductive elimination step. The iron core becomes super reduced and is able to bind to dinitrogen. Then proton transfer steps to that reduced nitrogen forms the bound diazine, and then steps E5 through E8 are productive hydrogen and electron transfer steps that generate first hydrazine and finally two equivalents of ammonia, regenerating the E0 state. In steps leading up to E5, the bridging hydride and the diazine undergo a migratory insertion, MI reaction, where the iron hydride ends up on the N2 position of the dinitrogen, of the diazine. And then in step E7, a similar migratory insertion occurs, followed by bond cleavage, BC, to release the ammonia, leaving an iron amide complex. And that step E8, the second ammonia is released, regenerating the E0 state. Important to note is that all of these states only have three formal oxidation states for this iron core, and really only two of them are observable. E0 is the reduced state, E1 is oxidized, which seems strange because we've added an electron and a proton, but remember that the hydride is storing the reducing equivalent. So in order to have an H-, we have to have a oxidation of the iron, and so we have actually oxidized the state. So it alternates between oxidized and reduced, oxidized and reduced. Then we do the reductive elimination to generate this super reduced iron, which is rapidly transferred back into the oxidized state. Subsequent electron proton transfer steps finally give the cluster back to reduce it down to form E0 back at the beginning of the process again. So thinking back to the organometallics unit, we've got a catalytic cycle. We have metals that are catalyzing this reaction. Electrons are coming from an alternate source, the Fe4S4 cluster in the iron protein, but we return the FeMO cofactor back to its original state at the end of the process. So we have a detailed mechanism of this enzyme process that's consistent with all of the data. The reducing equivalents do need to come from somewhere, and we want to make sure that those reducing equivalents are delivered to the FeMO cofactor and aren't shuttled backwards. And so one of the things that biology does really well is control the flow of electrons. So the relatively close proximity of the Fe4S4 cluster in the iron protein here and the P cluster and the FeMO cofactor here suggested electron transfer from this iron protein was important. So how does that take place in a controlled fashion? And what is the purpose of that ATP binding site? So a series of iron and iron molybdenum protein clusters were crystallized, and this first structure is the PCP derivative, which is a non-hydrolyzable magnesium ATP analog, and the structure of that is almost identical to what we saw in the last lecture on the aluminum tetrafluoride anion structure. So we have the iron protein and the iron molybdenum protein bound together. in this structure. This is the nucleotide-free version of the protein complex. So they crystallized this without any ATP molecules present. And then this structure is the one that contains an ADP that's already been hydrolyzed. In all three of these structures, there is not really a discernible structural change of the iron molybdenum protein, but there are significant changes both in the structure of the iron protein and its docking location on the iron molybdenum protein. And the iron molybdenum protein contains 3 docking sites on this side, in the middle, and then on this side to bind to these 3 different structures of the iron protein. I'm not going to go into the differences in the structure of the iron protein, but notice that there's a pretty substantial angle from -14 degrees to vertical to +12 degrees during this process. This angle and the structural changes in the iron protein actually cause a substantial difference in the distance between the Fe4S4 cluster in the iron protein and the P cluster in the iron molybdenum protein. So here at the start, we have the iron protein with no bound ATP. It's a nucleotide free, and you can see the distance between the Fe4S4 cluster and the P cluster is 23 angstroms. Binding of ATP, which is modeled by either the PCP or the aluminum fluoride model, changes the structure of the iron protein, changes the angle and the docking site, and brings this iron 4S4 cluster only 18 angstroms away from the P cluster. Finally, cleavage of the ATP to form ADP pulls the Fe4S4 cluster out here, which is again 23 to 24 angstroms away from the P cluster. Now, 18 angstroms is still a very long way for an electron to travel in a biological system, although you can see that the electron has to travel from the P cluster to the FeMO cofactor. That's 19 angstroms. And you can model electron transfer by tunneling, through space interactions, through protein chain interactions. And this graph is to show how rapidly electrons can transfer through either vacuum, water, or through a protein chain. And so as you include protein chains, like through bond interactions, that electron transfer can take place quite a bit faster. One of the homework problems for this week asks you to specifically look at the difference in electron transfer rate from a 23 angstrom distance to an 18 angstrom distance, and take a look at how much that rate increase takes place because of the ATP hydrolysis that takes place in the iron protein. So the iron protein binds ATP, causing an electron transfer process. The ATP is cleaved, which pulls that Fe4S4 cluster away. And so then the electron that has now been donated to the P cluster won't go back to the Fe4S4 cluster. Instead, it has to go forward to the iron molybdenum cofactor. And now we have a very complete picture of the reduction of dinitrogen by the nitrogenase enzyme complex. The reduced iron protein binds to the MOFE protein in the nucleotide-free state. As ATP binds to this protein, we get a 14-degree change in the angle, the bond angle, bringing the iron 4S4 cluster close to the P cluster, and electron transfer takes place. At that same time, or very close to the same time, ATP is hydrolyzed, causing further conformational changes, rocking by another 12 degrees, pulling that Fe4S4 cluster further away from the P cluster, preventing backwards flow of the electron. This transfer of an electron also takes place with the transfer of a proton, and this process has to take place 8 times in order to go through the entire LT model to go from state E0 to state E8. The dinitrogen binds at the Janus intermediate, state E4, and dihydrogen is reduced to, the 2 hydrides are reduced to dihydrogen at that step to form the super-reduced iron that can then bind to the dinitrogen. It's an incredible amount of work, and it's really an amazing story. I've been following nitrogenase for my entire professional career, and this has been a really exciting mechanism to watch unfold over the last 25 years of my life. And that's the mechanism. So the next thing we have to discover, which will begin the next lecture, is the binding of dinitrogen. We now know that the nitrogen binds to this Fe2, Fe6, Fe7, Fe3 face. How does the nitrogen get there? How does it get to that location in the protein? So the next lecture will explore a little bit about the pockets in the nitrogenase enzymes that allow for substrate going in and for product to leave.